Describe the composition of the atmosphere and the atmosphere's vertical changes in pressure and temperature. To better understand climate change, it is helpful to possess some basic knowledge about the composition and structure of the atmosphere. Composition of the atmosphere. Air is not a unique element or compound. Rather, air is a mixture of many discrete gases, each with its own physical properties, in which varying quantities of tiny solid and liquid particles are suspended. Clean, dry air. As you can see in Figure 20.9, clean, dry air is composed almost entirely of two gases, 78% nitrogen and 21% oxygen. Although these gases are the most plentiful components of air and are of great significance to life on Earth, they have little or no effect on weather phenomena. The remaining 1% of dry air is mostly the inert gas argon plus tiny quantities of a number of other gases. Carbon dioxide, although present in only minute amounts, is nevertheless an important constituent of air because it has the ability to absorb heat energy radiated by Earth and thus influences the heating of the atmosphere. Proportional volume of gases composing dry air. Nitrogen and oxygen obviously dominate. Smart Figure 20.9 Composition of the atmosphere. Smart Figure 20.9 Full alternative text description. Air includes many gases and particles that vary significantly from time to time and from place to place. Important examples include water vapor, ozone, and tiny solid and liquid particles. Water vapor. The amount of water vapor in the air varies considerably, from practically none at all up to about 4% by volume. Why is such a small fraction of the atmosphere so significant? Certainly the fact that water vapor is the source of all clouds and precipitation is enough to explain its importance. However, water vapor has other roles. Like carbon dioxide, it has the ability to absorb heat energy given off by Earth as well as some solar energy. It is, therefore, important when we examine the heating of the atmosphere. Ozone. Watch tutorial, Gases in the Atmosphere. Another important component of the atmosphere is ozone. It is a form of oxygen that combines 3 oxygen atoms into each molecule. Ozone is not the same as the oxygen we breathe, which has 2 atoms per molecule. There is very little ozone in the atmosphere, and its distribution is not uniform. It is concentrated well above Earth's surface, in a layer called the stratosphere, at an altitude of between 10 and 50 kilometers. The presence of the ozone layer in our atmosphere is crucial to those who dwell on Earth. Ozone absorbs the potentially harmful ultraviolet radiation from the sun. If ozone did not filter out a great deal of the ultraviolet radiation, and if the sun's UV rays reached the surface of Earth undiminished, our planet would be uninhabitable for most life as we know it. Aerosols. The movements of the atmosphere are sufficient to keep a large quantity of solid and liquid particles suspended within it. Although visible dust sometimes clouds the sky, these relatively large particles are too heavy to stay in the air very long. Still, many particles are microscopic and remain suspended for considerable periods of time. They may originate from many sources, both natural and human-made, and include sea salts from breaking waves, fine soil blown into the air, smoke and soot from fires, pollen and microorganisms lifted by the wind, ash and dust from volcanic eruptions, and more. Collectively, these tiny solid and liquid particles are called aerosols. From a meteorological standpoint, these tiny, often invisible particles can be significant. First, many act as surfaces on which water vapor can condense, an important function in the formation of clouds and fog. Second, aerosols can absorb or reflect incoming solar radiation. Thus, when an air pollution episode is occurring, or when ash fills the sky following a volcanic eruption, the amount of sunlight reaching Earth's surface can be measurably reduced. This satellite image shows 2 examples of aerosols. First, a dust storm is blowing across northeastern China toward the Korean peninsula. Second, a dense haze toward the south is human-generated air pollution. Smart Figure 20.10 Aerosols. Extent and structure of the atmosphere. To say that the atmosphere begins at Earth's surface and extends upward is obvious. But where does the atmosphere end, and where does outer space begin? There is no sharp boundary. The atmosphere rapidly thins as you travel away from Earth, until there are too few gas molecules to detect. Pressure changes with height. To understand the vertical extent of the atmosphere, let us examine changes in atmospheric pressure with height. Atmospheric pressure is simply the weight of the air above. At sea level, the average pressure is slightly more than 1,000 millibars. This corresponds to a weight of slightly more than 1 kilogram per square centimeter. Obviously, the pressure at higher altitudes is less. Watch video, Aerosols. Pressure decreases rapidly near Earth's surface and more gradually at greater heights. Figure 20.11 Full alternative text description. 1/2 of the atmosphere lies below an altitude of 5.6 kilometers. At about 16 kilometers, 90% of the atmosphere has been traversed, and above 100 kilometers, only 0.00003% of all the gases making up the atmosphere remains. Even so, traces of our atmosphere extend far beyond this altitude, gradually merging with the emptiness of space. Figure 20.11 Vertical changes in air pressure. Did you know? Although naturally occurring ozone in the stratosphere is critical to life on Earth, it is regarded as a pollutant when produced at ground level because it can damage vegetation and be harmful to human health. Ozone is a major component in a noxious mixture of gases and particles called photochemical smog. It forms as a result of reactions that are triggered by sunlight and occur among pollutants emitted by motor vehicles and industrial sources. Temperature changes. In addition to vertical changes in air pressure, there are also changes in air temperature as we ascend through the atmosphere. Earth's atmosphere is divided vertically into 4 layers, on the basis of temperature. Figure 20.12 Thermal structure of the atmosphere. Figure 20.12 Full alternative text description. Troposphere. The bottom layer, in which we live, is characterized by a decrease in temperature with increasing altitude and is called the troposphere. The term literally means the region where air turns over, a reference to the appreciable vertical mixing of air in this lowermost zone. The troposphere is the chief focus of meteorologists because it is in this layer that essentially all important weather phenomena occur. The temperature decrease in the troposphere is called the environmental lapse rate. Its average value is 6.5 degrees Celsius per kilometer, a figure known as the normal lapse rate. It should be emphasized, however, that the environmental lapse rate is not a constant. It varies over time and from one place to another and hence must be regularly measured. To determine the actual environmental lapse rate in a particular place and time, as well as to gather information about vertical changes in pressure, wind, and humidity, radiosondes are used. A radiosonde is an instrument package that is attached to a weather balloon and transmits data by radio as it ascends through the atmosphere. The thickness of the troposphere is not the same everywhere, it varies with latitude and the season. On average, the drop in temperature that defines the troposphere continues to a height of about 12 kilometers. The outer boundary of the troposphere is the tropopause. A radiosonde is a lightweight package of instruments that is carried aloft by a small weather balloon. It transmits data on vertical changes in temperature, pressure, and humidity in the troposphere. The troposphere is where practically all weather phenomena occur, therefore, it is very important to have frequent measurements. Figure 20.13 Radiosonde. Stratosphere. Beyond the tropopause is the stratosphere. In the stratosphere, the temperature remains constant to a height of about 20 kilometers and then begins a gradual increase that continues until the stratopause, at a height of nearly 50 kilometers above Earth's surface. Below the tropopause, atmospheric properties such as temperature and humidity are readily transferred by large-scale turbulence and mixing. Above the tropopause, in the stratosphere, they are not. Temperatures increase in the stratosphere because it is in this layer that the atmosphere's ozone is concentrated. Recall that ozone absorbs ultraviolet radiation from the sun. As a consequence, the stratosphere is heated. Mesosphere. In the third layer, the mesosphere, temperatures again decrease with height until, at the mesopause, more than 80 kilometers above the surface, the temperature approaches 90 degrees C. The coldest temperatures anywhere in the atmosphere occur at the mesopause. Thermosphere. The fourth layer extends outward from the mesopause and has no well-defined upper limit. This is the thermosphere, a layer that contains only a tiny fraction of the atmosphere's mass. In the extremely rarefied air of this outermost layer, temperatures again increase, due to the absorption of very short-wave, high-energy solar radiation by atoms of oxygen and nitrogen. Temperatures rise to extremely high values of more than 1000 degrees Celsius in the thermosphere. But such temperatures are not comparable to those experienced near Earth's surface. Temperature is defined in terms of the average speed at which molecules move. Because the gases of the thermosphere are moving at very high speeds, the temperature is very high. But the gases are so sparse that, collectively, they possess only an insignificant amount of heat. Concept checks 20.3. 1. What are the major components of clean, dry air? List 2 significant variable components. 2. Describe how air pressure changes with an increase in altitude. Does it change at a constant rate? 3. The atmosphere is divided vertically into 4 layers, on the basis of temperature. Name the layers from bottom to top and indicate how temperatures change in each. 20.4 Heating the atmosphere. Outline the basic processes involved in heating the atmosphere. Nearly all the energy that drives Earth's variable weather and climate comes from the sun. Before we can adequately describe how Earth's atmosphere is heated, it is helpful to know something about solar energy and what happens to this energy once it is intercepted by Earth. Energy from the sun. From our everyday experience, we know that the sun emits light and heat as well as the ultraviolet rays that cause suntan. Although these forms of energy comprise a major portion of the total energy that radiates from the sun, they are only part of a large array of energy called radiation, or electromagnetic radiation. This array, or spectrum, of electromagnetic energy is shown in Figure 20.14. All radiation, whether X-rays, microwaves, or radio waves, transmits energy through the vacuum of space at 300,000 kilometers per second and only slightly slower through our atmosphere. When an object absorbs any form of radiant energy, the result is an increase in molecular motion, which causes a corresponding increase in temperature. This diagram illustrates the wavelengths and names of various types of radiation. Visible light consists of an array of colors we commonly call the colors of the rainbow. Smart Figure 20.14 The electromagnetic spectrum. Smart Figure 20.14 Full alternative text description. To better understand how the atmosphere is heated, it is useful to have a general understanding of the basic laws governing radiation. Watch video, The Electromagnetic Spectrum. All objects, at whatever temperature, emit radiant energy. Not only hot objects like the sun but also Earth, including its polar ice caps, continually emit energy. Hotter objects radiate more total energy per unit area than do colder objects. The hotter the radiating body, the shorter the wavelength of maximum radiation. The sun, with a surface temperature of about 5,700 degrees Celsius, radiates maximum energy at 0.5 micrometer, which is in the visible range. The maximum radiation for Earth occurs at a wavelength of 10 micrometers, well within the infrared range. Because the wavelength for maximum Earth radiation is roughly 20 times longer than the maximum solar radiation, Earth radiation is often called long-wave radiation, and solar radiation is called short-wave radiation. Objects that are good absorbers of radiation are good emitters as well. Earth's surface and the Sun approach being perfect radiators because they absorb and radiate with nearly 100% efficiency for their respective temperatures. On the other hand, gases are selective absorbers and emitters of radiation. For some wavelengths, the atmosphere is nearly transparent. For other wavelengths, however, the atmosphere is nearly opaque. Experience tells us that the atmosphere is transparent to visible light, hence, these wavelengths readily reach Earth's surface. This is not the case for the longer wavelength radiation emitted by Earth. The paths of incoming solar energy. Figure 20.15 shows the paths taken by incoming solar radiation averaged for the entire globe. Notice that the atmosphere is quite transparent to incoming solar radiation. On average, about 50% of the solar energy reaching the top of the atmosphere passes through the atmosphere and is absorbed at Earth's surface. Another 20% is absorbed directly by clouds and certain atmospheric gases before reaching the surface. The remaining 30% is reflected back to space by the atmosphere, clouds, and reflective surfaces such as snow and ice. The fraction of the total radiation that is reflected by a surface is called its albedo. Thus, the albedo for Earth as a whole is 30%. This diagram shows the average distribution of incoming solar radiation by percentage. More solar radiation is absorbed by Earth's surface than by the atmosphere. Smart figure 20.15 paths taken by solar radiation. Smart figure 20.15 full alternative text description. In general, light-colored surfaces tend to be more reflective than dark-colored surfaces and thus have higher albedos. Watch tutorial, Solar Radiation Paths. Figure 20.16 albedo of various surfaces. Figure 20.16 full alternative text description. What determines whether solar radiation will be transmitted to the surface, scattered, or reflected outward? It depends greatly on the wavelength of the energy being transmitted, as well as on the nature of the intervening material. The numbers shown in figure 20.15 represent global averages. The actual percentages at different times and locations vary greatly, primarily due to changes in the percentage of light reflected and scattered back to space. For example, if the sky is overcast, a higher percentage of light is reflected back to space than when the sky is clear. Heating the atmosphere, the greenhouse effect. If Earth had no atmosphere, it would experience an average surface temperature far below freezing. But the atmosphere warms the planet and makes Earth livable. The extremely important role the atmosphere plays in heating Earth's surface has been named the greenhouse effect. As discussed earlier, cloudless air is largely transparent to incoming shortwave solar radiation and, hence, transmits it to Earth's surface. By contrast, a significant fraction of the long-wave radiation emitted by Earth's land, sea surface is absorbed by water vapor, carbon dioxide, and other trace gases in the atmosphere. This energy heats the air and increases the rate at which it radiates energy, both out to space and back toward Earth's surface. Without this complicated game of pass the hot potato, Earth's average temperature would be 18 degrees Celsius, rather than the current average temperature of 15 degrees Celsius, figure 20. 17. These absorptive gases in our atmosphere make Earth habitable for humans and other life forms. As you will see in the sections that follow, changes in the air's composition, both natural and human-caused, impact the greenhouse effect in ways that can cause the atmosphere to either become warmer or cooler. Smart figure 20.17 The greenhouse effect. The greenhouse effect of Earth compared with two of our close solar system neighbors. Smart figure 20.17 Full alternative text description. Watch tutorial, 3 planets, 3 climates. The greenhouse effect was so named because greenhouses are warmed in part by a similar phenomenon. The glass in a greenhouse allows shortwave solar radiation to enter and be absorbed by the objects inside. These objects radiate energy at longer wavelengths, to which glass is nearly opaque. The heat, therefore, is trapped in the greenhouse. In reality, The major reason air in a greenhouse warms is because the glass restricts exchange with cooler air outside. Nevertheless, the term greenhouse effect remains. Concept checks 20.4. 1. What are the three paths that incoming solar radiation takes? What might cause the percentage taking each path to vary? 2. Explain why the atmosphere is heated chiefly by radiation from Earth's surface. 3. Prepare a sketch with labels that explains the greenhouse effect. 20.5 Natural causes of climate change. Discuss hypotheses that relate to natural causes of climate change. A great variety of hypotheses have been proposed to explain climate change. Several have gained wide support, only to lose it and then sometimes to regain it. Some explanations are controversial. This is to be expected because planetary atmospheric processes are so large-scale and complex that they cannot be reproduced physically in laboratory experiments. Rather, climate and its changes must be simulated mathematically, using powerful computers. In this section we examine several current hypotheses that have earned serious consideration from the scientific community. They describe natural mechanisms of climatic change, causes that are unrelated to human activities. A later section examines human-induced climate changes, including the effect of rising carbon dioxide levels caused primarily by our burning of fossil fuels. As you read this section, you will find that more than one hypothesis may explain the same change in climate. In fact, several mechanisms may interact to shift climate. Also, no single hypothesis can explain climate change on all time scales. A proposal that explains variations over millions of years generally cannot explain fluctuations over hundreds of years. If our atmosphere and its changes ever become fully understood, we will probably see that climate change is caused by many of the mechanisms discussed here, plus new ones yet to be proposed. Plate movements and orbital variations. In Chapter 15, the section, Causes of Ice Ages, describes two natural mechanisms of climate change. Recall that the movement of lithospheric plates gradually moves Earth's continents closer to or farther from the equator. Although these shifts in plates are very slow, they can have a dramatic impact on climate over spans of millions of years. Moving land masses can also lead to significant shifts in ocean circulation, which influences heat transport around the globe. A second natural mechanism of climate change related to the causes of ice ages involves variations in Earth's orbit. Changes in the shape of the orbit. Variations in the angle that Earth's axis makes with the plane of its orbit, and the wobbling of the axis cause fluctuations in the seasonal and latitudinal distribution of solar radiation. These variations, in turn, contributed to the alternating glacial, interglacial episodes of the Ice Age. Did you know? A meteorite colliding with Earth could trigger climate change. For example, the most strongly supported hypothesis for the extinction of dinosaurs is related to such an event. When a large meteorite struck Earth, huge quantities of debris were blasted high into the atmosphere. For months the encircling dust cloud greatly restricted the amount of light reaching Earth's surface. Without sufficient sunlight for photosynthesis, delicate food chains collapsed. When the sunlight returned, more than half of the species on Earth, including the dinosaurs and many marine organisms, had become extinct. There is more about this in Chapter 19. Volcanic activity and climate change. The idea that explosive volcanic eruptions might alter Earth's climate was first proposed many years ago. It is still regarded as a plausible explanation for some aspects of climatic variability. Explosive eruptions emit huge quantities of gases and fine-grained debris into the atmosphere. The greatest eruptions are sufficiently powerful to inject material high into the atmosphere, and strong upper air winds spread it around the globe, where it remains for many months or even years. This volcano on the island of Sicily is Europe's largest and most active volcano. Figure 20.18 Full alternative text description. Figure 20.18 Mount Etna erupting in October 2002. The effect of volcanic aerosols on climate. Suspended volcanic material filters out a portion of the incoming solar radiation, which in turn lowers temperatures in the troposphere. More than 200 years ago, Benjamin Franklin used this idea to argue that material from the eruption of a large Icelandic volcano could have reflected sunlight back to space and therefore might have been responsible for the unusually cold winter of 1783-1784. Perhaps the most notable cool period linked to a volcanic event is the year without a summer that followed the 1815 eruption of Mount Tambora in Indonesia. The eruption of Tambora is the largest of modern times. During April 7–12, 1815, this nearly 4,000-meter-high volcano violently expelled an estimated 100 cubic kilometers of volcanic debris. The impact of the volcanic aerosols on climate is believed to have been widespread in the northern hemisphere. From May through September 1816, an unprecedented series of cold spells affected the northeastern United States and adjacent portions of Canada. There was heavy snow in June and frost in July and August. Abnormal cold was also experienced in much of Western Europe. Similar, although apparently less dramatic, effects have been associated with other great explosive volcanoes, including Indonesia's Krakatoa in 1883. Three more recent volcanic events have provided considerable data and insight regarding the impact of volcanoes on global temperatures. The eruptions of Washington State's Mount St. Helens in 1980, the Mexican volcano El Chichón in 1982, and Mount Pinatubo in the Philippines in 1991 have given scientists opportunities to study the atmospheric effects of volcanic eruptions with the aid of more sophisticated technology than was previously available. Satellite images and remote sensing instruments allowed scientists to closely monitor the effects of the clouds of gases and ash that these volcanoes emitted. Volcanic ash and dust. When Mount St. Helens erupted, there was immediate speculation about the possible effects on climate. Could such an eruption cause our climate to change? There is no doubt that the large quantity of volcanic ash emitted by the explosive eruption had significant local and regional effects for a short period. Still, studies indicated that any longer-term lowering of hemispheric temperatures was negligible. The cooling was so slight, probably less than 0.1 degrees Celsius, that it could not be distinguished from other natural temperature fluctuations. Sulfuric acid droplets. 2 years of monitoring and studies following the 1982 El Chichón eruption indicated that it had a greater cooling effect on global mean temperature than Mount St. Helens, on the order of 0.3 degrees to 0.5 degrees Celsius. El Chichón's eruption was less explosive than the Mount St. Helens blast, so why did it have a greater impact on global temperatures? The reason is that the material emitted by Mount St. Helens was largely fine ash that settled out in a relatively short time. El Chichón, on the other hand, emitted far greater quantities of sulfur dioxide gas than Mount St. Helens. This gas combines with water vapor in the stratosphere to produce a dense cloud of tiny sulfuric acid particles. These particles take several years to settle out completely. They lower the troposphere's mean temperature because they reflect solar radiation back to space. The reflective haze produced by some volcanic eruptions is not volcanic ash but tiny sulfuric acid aerosols. Figure 20.19 Volcanic haze reducing sunlight at Earth's surface. Figure 20.19 Full alternative text description. We now understand that volcanic clouds that remain in the stratosphere for a year or more are composed largely of sulfuric acid droplets and not of dust, as was once thought. Thus, the volume of fine debris emitted during an explosive event is not an accurate criterion for predicting the global atmospheric effects of an eruption. Mount Pinatubo in the Philippines erupted explosively in June 1991, injecting 25 to 30 million tons of sulfur dioxide into the stratosphere. The event provided scientists with an opportunity to study the climatic impact of a major explosive volcanic eruption using NASA's Spaceborne Earth Radiation Budget experiment. During the next year, the haze of tiny aerosols increased reflectivity and lowered global temperatures by 0.5 degrees Celsius. The impact on global temperature of eruptions like El Chichón and Mount Pinatubo is relatively minor, but many scientists agree that the cooling produced could alter the general pattern of atmospheric circulation for a limited period. Such a change could, in turn, influence the weather in some regions. Predicting, or even identifying, specific regional effects still presents a considerable challenge to atmospheric scientists. The preceding examples illustrate that the impact on climate of a single volcanic eruption, no matter how great, is relatively small and short-lived. The graph in Figure 20.19b reinforces this point. Therefore, if the processes discussed in this section are to have a pronounced impact over an extended period, many great eruptions, closely spaced in time, need to occur. Because no such period of explosive volcanism is known to have occurred in historic times, it is most often mentioned as a possible contributor to prehistoric climatic shifts. Volcanism and global warming. The Cretaceous period is the last period of the Mesozoic era, the era of middle life that is often called the Age of Dinosaurs. It began about 145.5 million years ago and ended about 65.5 million years ago, with the extinction of the dinosaurs. The Cretaceous climate was among the warmest in Earth's long history. Dinosaurs, which are associated with mild temperatures, ranged north of the Arctic Circle. Tropical forests existed in Greenland and Antarctica, and coral reefs grew as much as 15 degrees latitude closer to the poles than at present. Deposits of peat that would eventually form widespread coal beds accumulated at high latitudes. Sea level was as much as 200 meters higher than it is today, consistent with a lack of polar ice sheets as well as with an abundance of active and hence high-standing oceanic ridges. What caused the unusually warm climates of the Cretaceous period? Among the significant factors that may have contributed was an enhanced greenhouse effect due to an increase in the amount of carbon dioxide in the atmosphere. But where did the additional CO2 come from? Many geologists suggest that the probable source was volcanic activity. Carbon dioxide is one of the gases emitted during volcanism, and there is now considerable geologic evidence that the Middle Cretaceous was a time of an unusually high rate of volcanic activity. Several huge oceanic lava plateaus were produced on the floor of the western Pacific during this span. These vast features were associated with hot spots that may have been produced by large mantle plumes. Massive outpourings of lava over millions of years would have been accompanied by the release of huge quantities of CO2, which in turn would have enhanced the atmospheric greenhouse effect. Thus, the warmth that characterized the Cretaceous may have had its origins deep in Earth's mantle. This example illustrates the interrelationships among parts of the Earth system. Seemingly unrelated materials and processes turn out to be linked. Here you have seen how processes originating deep in Earth's interior are connected directly or indirectly to the atmosphere, the oceans, and the biosphere. Solar variability and climate. Among the most persistent hypotheses of climate change have been those based on the idea that the Sun is a variable star and that its energy output varies through time. The effect of such changes would seem direct and easily understood. Increases in solar output would cause the atmosphere to warm, and reductions would result in cooling. This notion is appealing because it can be used to explain climate change of any length or intensity. However, no major long-term variations in the total intensity of solar radiation have yet been measured outside the atmosphere. Such measurements were not even possible until satellite technology became available. We can now measure solar output, but we still need many decades of records before we begin to sense how variable energy from the Sun really is. Some hypotheses for climate change relate to sunspot cycles. The most conspicuous and best-known features on the surface of the Sun are the dark blemishes called sunspots. Sunspots are huge magnetic storms that extend from the Sun's surface deep into the interior. Moreover, these spots are associated with the Sun's ejection of huge masses of particles that, on reaching Earth's upper atmosphere, interact with gases to produce displays known as the aurora borealis, or northern lights, in the northern hemisphere. Both images show sunspot activity at the same location on the solar disk at the same time on March 5, 2012, using two different instruments from NASA's Solar Dynamics Observatory. Smart Figure 20.20 Full Alternative Text Description. Smart Figure 20.20 Sunspots. Sunspots occur in cycles, with the number of sunspots reaching a maximum about every 11 years. During periods of maximum sunspot activity, the sun emits slightly more energy than during sunspot minimums. Based on measurements from space that began in 1978, the variation during an 11-year cycle is about 0.1%. Although sunspots are dark, they are surrounded by brighter areas, which apparently offsets the effect of the dark spots. It appears that this change in solar output is too small and the cycles are too short to have any appreciable effect on global temperatures. However, there is a possibility that longer-term variations in solar output may affect climates on Earth. The number of sunspots reaches a maximum about every 11 years. Watch video. NASA, giant sunspot continues to erupt with substantial flares. Figure 20.21 Mean annual sunspot numbers. Figure 20.21 Full alternative text description. For example, the span between 1645 and 1715 is a period, known as the Maunder minimum, during which sunspots were largely absent. This period of missing sunspots closely corresponds with a period in climate history known as the Little Ice Age, an especially cold period in Europe. For some scientists, this correlation suggests that a reduction in the sun's output was likely responsible at least in part for this cold episode. Other scientists seriously question this notion. Their hesitation stems, in part, from subsequent investigations using different climate records from around the world that failed to find a significant correlation between sunspot activity and climate. Did you know? Based on recent research that used satellite data, there appears to be no connection between changes in the sun's brightness and recent global warming. The scientists who carried out this detailed analysis state that variations in solar brightness measured since 1978, which is as far back as these measurements go, are too small to have contributed appreciably to accelerated global warming over the past 30 years. Concept checks 20.5. 1. Describe and briefly explain the effect on global temperatures of the eruptions of El Chichón and Mount Pinatubo. 2. How might volcanism lead to global warming? 3. What are sunspots? How does solar output change as sunspot numbers change? Is there a solid connection between sunspot numbers and climate change on Earth? For more on this, see the section Supercontinents, Mountain Building, and Climate in Chapter 19. For more about the end of the Cretaceous, see Chapter 19. 20.6 Human impact on global climate. Summarize the nature and cause of the atmosphere's changing composition since about 1750. Describe the climate's response. So far we have examined potential causes of climate change that are natural. In this section, we examine how humans contribute to global climate change. One impact largely results from the addition of carbon dioxide and other greenhouse gases to the atmosphere. A second impact is related to the addition of human-generated aerosols to the atmosphere. Human influence on regional and global climate did not just begin with the onset of the modern industrial period. There is good evidence that people have been modifying the environment over extensive areas for thousands of years. The use of fire and the overgrazing of marginal lands by domesticated animals have both reduced the abundance and distribution of vegetation. By altering ground cover, humans have modified such important climate factors as surface albedo, evaporation rates, and surface winds. Rising CO2 levels. Earlier you learned that carbon dioxide CO2 represents only about 0.0400% of the gases that make up clean, dry air. Nevertheless, it is a very significant component meteorologically. Carbon dioxide is influential because it is transparent to incoming short-wavelength solar radiation, but it is not transparent to some of the longer wavelength outgoing Earth radiation. A portion of the energy leaving Earth's surface is absorbed by atmospheric CO2. This energy is subsequently re-emitted, part of it back toward the surface, thereby keeping the air near the ground warmer than it would be without CO2. Thus, along with water vapor, carbon dioxide is largely responsible for the atmosphere's greenhouse effect. The tremendous industrialization of the past 2 centuries has been fueled, and still is fueled, by burning fossil fuels, coal, natural gas, and petroleum. Combustion of these fuels has added great quantities of carbon dioxide to the atmosphere. Figure 20. 23 shows changes in CO2 concentrations at Hawaii's Mauna Loa Observatory, where measurements have been made since 1958. The graph shows an annual seasonal cycle and a steady upward trend over the years. The up and down of the seasonal cycle is due to the vast land area of the Northern Hemisphere, which contains the majority of land-based vegetation. During spring and summer in the Northern Hemisphere, when plants are absorbing CO2 as part of photosynthesis, concentrations decrease. The annual increase in atmospheric CO2 during the cold months occurs as vegetation dies and leaves fall and decompose, releasing CO2 back into the air. The graph shows energy consumption in 2015. The total was 97.65 quadrillion BTU. A quadrillion is 10 raised to the 15th power, or a billion million. The burning of fossil fuels represents about 81.3% of the total. Figure 20.22 Full alternative text description. Atmospheric CO2 has been measured at Mauna Loa Observatory, Hawaii, since 1958. There has been a consistent increase since monitoring began. This graphic portrayal is known as the Keeling curve, in honor of the scientist who originated the measurements. Figure 20.22 U.S. energy consumption. Smart Figure 20.23 Monthly CO2 concentrations. Smart Figure 20.23 Full alternative text description. The use of coal and other fuels is the most prominent means by which humans add CO2 to the atmosphere, but it is not the only way. The clearing of forests also contributes substantially because CO2 is released as vegetation is burned or decays. Deforestation is particularly pronounced in the tropics, where vast tracts are cleared for ranching and agriculture, or subjected to inefficient commercial logging operations. All major tropical forests, including those in South America, Africa, Southeast Asia, and Indonesia, are disappearing. According to United Nations estimates, more than 10 million hectares of tropical forest were permanently destroyed each year during the decades of the 1990s and 2000s, although this rate has slowed in recent years. Watch tutorial, the Mauna Loa CO record. Clearing of the tropical rainforest is a serious environmental issue. In addition to causing a loss of biodiversity, it is a significant source of carbon dioxide. Fires are frequently used to clear the land. This scene is in Brazil's Amazon basin. Some of the excess CO2 is taken up by plants or is dissolved in the ocean, but an estimated 45% remains in the atmosphere. Figure 20.25 is a graphic record of changes in atmospheric CO2 extending back 800,000 years. Over this long span, natural fluctuations have varied from about 180 to 300 ppm. As a result of human activities, the present CO2 level is more than 30% higher than its highest level over at least the past 800,000 years. The rapid increase in CO2 concentrations since the onset of industrialization is obvious. The annual rate at which atmospheric CO2 concentrations are growing has been increasing over the past several decades. Figure 20.24 Tropical deforestation. Most of these data come from the analysis of air bubbles trapped in ice cores. The record since 1958 comes from direct measurements at Mauna Loa Observatory, Hawaii. The rapid increase in CO2 concentrations since the onset of the Industrial Revolution is obvious. Figure 20.25 Full alternative text description. The atmosphere's response. Figure 20.25 CO concentrations over the past 800,000 years. Given the increase in the atmosphere's CO2 content, have global temperatures actually increased? The answer is yes. According to a 2013 report by the Intergovernmental Panel on Climate Change, warming of the climate system is unequivocal, as is now evident from observations of increases in global average air and ocean temperatures, widespread melting of snow and ice, and rising global sea level. Most of the observed increase in global average temperatures since the mid-20th century is extremely likely due to the observed increase in human-generated greenhouse gas concentrations. As used by the IPCC, extremely likely indicates a probability of 95 to 100%. The planet's average surface air temperature has risen about 1 degree Celsius since the late 19th century, with most of the warming occurring in the past 35 years. 15 of the 16 warmest years on record have occurred since 2001. Surface air temperatures in 2015 were the warmest since record-keeping began in 1880, shattering the mark set in 2014. IPCC, Summary for Policymakers, in Climate Change 2013, The Physical Science Basis. The Intergovernmental Panel on Climate Change is an authoritative group of scientists that provides advice to the world community through periodic reports that assess the state of knowledge of the causes and effects of climate change. A. The world map shows how average temperatures in 2015 deviated from the mean for the 1951-1980 base period. The high latitudes in the northern hemisphere clearly stand out. B. The decade-by-decade temperature trend since 1950 is illustrated in this bar graph. Continued increases in the atmosphere's greenhouse gas levels are driving a long-term increase in global temperatures. Each calendar year is not necessarily warmer than the year before, but since 1950, each decade has been warmer than the previous one. Smart Figure 20.26 Global Temperatures. Smart Figure 20.26 Full alternative text description. Watch video, NASA, 2014, the warmest year on record. Weather patterns and other natural cycles cause fluctuations in average temperatures from year to year. This is especially true on regional and local levels. For example, while the globe experienced notably warm temperatures in 2014, parts of the continental United States were cooler than normal. By contrast, 2014 was the warmest year on record for much of Europe and parts of Russia, and ocean temperatures were at a record high. Regardless of regional differences in any year, increases in greenhouse gas levels are causing a long-term rise in global temperatures. Although each calendar year will not necessarily be warmer than the one before, scientists expect each decade to be warmer than the previous one. An examination of the decade-by-decade temperature trend in Figure 20.26b bears this out. What about the future? Projections for the years ahead depend in part on the quantities of greenhouse gases that are emitted. Figure 20.27 shows the best estimates of global warming for several different scenarios. The 2013 IPCC report states that if there is a doubling of the pre-industrial level of carbon dioxide to 560 ppm, the likely temperature increase will be in the range of 2 degrees to 4.5 degrees Celsius. The increase is very unlikely to be less than 1.5 degrees Celsius, and values higher than 4.5 degrees Celsius are possible. The right half of the graph shows projected global warming based on different emissions scenarios. The shaded zone adjacent to each colored line shows the uncertainty range for each scenario. The basis for comparison is the global average for the period 1980 to 1999. The orange line represents the scenario in which CO2 concentrations were held constant at values for the year 2000. Smart Figure 20.27 Temperature projections to 2100. Smart Figure 20.27 Full alternative text description. The role of trace gases. Watch video, Taking Earth's Temperature. Carbon dioxide is not the only gas contributing to a global increase in temperature. In recent years, atmospheric scientists have come to realize that human industrial and agricultural activities are causing a buildup of several trace gases that also play significant roles. The substances are called trace gases because their concentrations are much lower than the concentration of carbon dioxide. The most important trace gases are methane, nitrous oxide, and chlorofluorocarbons. These gases absorb wavelengths of outgoing radiation from Earth that would otherwise escape into space. Although individually their impact is modest, taken together these trace gases play a significant role in warming the troposphere. Methane. Although present in much smaller amounts than CO2, methane's significance is greater than its relatively small concentration would indicate. This is because methane is about 20 times more effective than CO2 at absorbing infrared radiation emitted by Earth. Although CO2 is most important, these trace gases also contribute to global warming. Over the 2,000-year span shown here, there were relatively minor fluctuations until the industrial era. The graph on the right shows recent trends. Figure 20.28 Methane and nitrous oxide. Figure 20.28 Full alternative text description. Methane is produced by anaerobic bacteria in wet places where oxygen is scarce. Such places include swamps, bogs, wetlands, and the guts of termites and grazing animals such as cattle and sheep. Methane is also generated in flooded paddy fields used for growing rice. Mining of coal and drilling for oil and natural gas are other sources because methane is a product of their formation. The increase in the concentration of methane in the atmosphere has been in step with the growth in human population. This relationship reflects the close link between methane formation and agriculture. As population increases, so do the number of cattle and rice paddies. Nitrous oxide. Sometimes called laughing gas, nitrous oxide is also building in the atmosphere, although not as rapidly as methane. The increase results primarily from agricultural activity. When farmers use nitrogen fertilizers to boost crop yield, some of the nitrogen enters the air as nitrous oxide. This gas is also produced by high-temperature combustion of fossil fuels. Although the annual release into the atmosphere is small, nitrous oxide is about 300 times more effective than CO2 as a greenhouse gas. Also, the average residence time of a nitrous oxide molecule in the atmosphere is about 114 years. If nitrogen fertilizer and fossil fuel use grow at projected rates, nitrous oxide's contribution to greenhouse warming may approach half that of methane. CFCs. Unlike methane and nitrous oxide, chlorofluorocarbons are not naturally present in the atmosphere. CFCs are manufactured chemicals with many uses that have gained notoriety because they are responsible for ozone depletion in the stratosphere. The role of CFCs in global warming is less well known. CFCs are very effective greenhouse gases. They were not developed until the 1920s and were not used in great quantities until the 1950s. Although corrective action has been taken, CFC levels will not drop rapidly. CFCs remain in the atmosphere for decades, so even though CFC emissions by developed nations have essentially ceased, the atmosphere will not be free of them for many years. A combined effect. Carbon dioxide is clearly the most important single cause for the projected global greenhouse warming. However, it is not the only contributor. When the effects of all human-generated greenhouse gases other than CO2 are added together and projected into the future, their collective impact significantly increases the impact of CO2 alone. Sophisticated computer models show that the warming of the lower atmosphere caused by CO2 and trace gases will not be the same everywhere. Rather, the temperature response in polar regions could be 2 to 3 times greater than the global average. Because the polar troposphere is very stable, vertical mixing is suppressed, which limits the amount of surface heat that is transferred upward. In addition, an expected reduction in sea ice would contribute to the greater temperature increase. This topic will be explored more fully in the next section. Did you know? The Intergovernmental Panel on Climate Change referred to in the discussion of global warming was established by the United Nations Environment Programme and the World Meteorological Organization in 1988 to assess the scientific, technical, and socio-economic information that is relevant to understanding climate change. It is an authoritative group that provides periodic reports regarding the state of knowledge about causes and effects of climate change. More than 250 authors and nearly 1,100 scientific reviewers from 55 countries contributed to Climate Change 2013, the physical science basis. How aerosols influence climate. Increasing the levels of carbon dioxide and other greenhouse gases in the atmosphere is the most direct human influence on global climate. But it is not the only impact. Global climate is also affected by human activities that contribute to the atmosphere's aerosol content. Recall that aerosols are the tiny, often microscopic, liquid and solid particles that are suspended in the air. Unlike cloud droplets, aerosols are present even in relatively dry air. Atmospheric aerosols are composed of many different materials, including soil, smoke, sea salt, and sulfuric acid. Natural sources are numerous and include such phenomena as dust storms and volcanoes. Most human-generated aerosols come from two sources: sulfur dioxide emitted during the combustion of fossil fuels and smoke from vegetation burned to clear agricultural land. Chemical reactions in the atmosphere convert the sulfur dioxide into sulfate aerosols, the same material that produces acid precipitation. The satellite images in Figure 20.29 provide an example. These satellite images show a serious air pollution episode that plagued China on October 8, 2010. Figure 20.29 Full alternative text description. Figure 20.29 Human-generated aerosols. How do aerosols affect climate? Aerosols act directly by reflecting sunlight back to space and indirectly by making clouds brighter reflectors. The second effect relates to the fact that many aerosols attract water and thus are especially effective as cloud condensation nuclei. The large quantities of aerosols produced by human activities trigger an increase in the number of cloud droplets that form within a cloud. A greater number of small droplets increases the cloud's brightness, causing more sunlight to be reflected back to space. One category of aerosols, called black carbon, is soot generated by combustion processes and fires. Unlike most other aerosols, black carbon warms the atmosphere because it is an effective absorber of incoming solar radiation. In addition, when deposited on snow and ice, black carbon reduces surface albedo, thus increasing the amount of light absorbed. Nevertheless, despite the warming effect of black carbon, the overall effect of atmospheric aerosols is to cool Earth. Studies indicate that the cooling effect of human-generated aerosols offsets a portion of the global warming caused by the growing quantities of greenhouse gases in the atmosphere. The magnitude and extent of the cooling effect of aerosols is uncertain. This uncertainty is a significant hurdle in advancing our understanding of how humans alter Earth's climate. It is important to point out some significant differences between global warming by greenhouse gases and aerosol cooling. After being emitted, carbon dioxide and trace gases remain in the atmosphere for many decades. By contrast, aerosols released into the troposphere remain there for only a few days or, at most, a few weeks before they are washed out by precipitation, limiting their effects. Because of their short lifetime in the troposphere, aerosols are distributed unevenly over the globe. As expected, human-generated aerosols are concentrated near the areas that produce them, namely industrialized regions that burn fossil fuels and places where vegetation is burned. Concept checks 20.6. 1. Why has the CO2 level of the atmosphere been increasing over the past 200 years? 2. How has the atmosphere responded to the growing CO2 levels? How are temperatures in the lower atmosphere likely to change as CO2 levels continue to increase? 3. Aside from CO2, what trace gases are contributing to global temperature change? 4. List the main sources of human-generated aerosols and describe their net effect on atmospheric temperatures. 20.7 Climate feedback mechanisms. Contrast positive and negative feedback mechanisms and provide examples of each. Climate is a very complex interactive physical system. Thus, when any component of the climate system is altered, scientists must consider many possible outcomes. These possible outcomes are called climate feedback mechanisms. They complicate climate modeling efforts and add uncertainty to climate predictions. Types of feedback mechanisms. What climate feedback mechanisms are related to carbon dioxide and other greenhouse gases? One important mechanism is that warmer surface temperatures increase evaporation rates. This, in turn, increases the water vapor in the atmosphere. Remember that water vapor is an even more powerful absorber of radiation emitted by Earth than is carbon dioxide. Therefore, with more water vapor in the air, the temperature increase caused by carbon dioxide and trace gases is reinforced. Scientists who model global climate change indicate that the temperature increase at high latitudes may be 2 to 3 times greater than the global average. This assumption is based in part on the likelihood that the area covered by sea ice will decrease as surface temperatures rise. Because ice reflects a much larger percentage of incoming solar radiation than does open water, the melting of sea ice replaces a highly reflective surface with a relatively dark surface. The result is a substantial increase in the solar energy absorbed at the surface. This in turn feeds back to the atmosphere and magnifies the initial temperature increase created by higher levels of greenhouse gases. The image shows the springtime breakup of sea ice near Antarctica. The diagram shows a likely feedback loop. A reduction in sea ice acts as a positive feedback mechanism because surface albedo decreases, and the amount of energy absorbed at the surface increases. Smart Figure 20.30 Sea ice as a feedback mechanism. The climate feedback mechanisms discussed thus far magnify the temperature rise caused by the buildup of greenhouse gases. Because these effects reinforce the initial change, they are called positive feedback mechanisms. On the other hand, negative feedback mechanisms produce results that are just the opposite of the initial change and tend to offset it. Watch video, NASA, The World is Black and White. One probable result of a global temperature rise would be an accompanying increase in cloud cover due to the higher moisture content of the atmosphere. Most clouds are good reflectors of solar radiation. At the same time, however, they are also good absorbers and emitters of radiation emitted by Earth. Consequently, clouds produce two opposite effects. They exert a negative feedback because they increase Earth's albedo and thus reduce the amount of solar energy available to heat the atmosphere. On the other hand, clouds exert a positive feedback by absorbing and emitting radiation that would otherwise be lost from the troposphere. Which effect, if either, is stronger? Observations and modeling demonstrate that the overall effect of clouds is to slightly cool the planet. This means that the warming caused by the buildup of greenhouse gases is slightly offset by the increase in cloud cover. The problem of global warming caused by human-induced changes in atmospheric composition continues to be one of the most studied aspects of climate change. Although no models yet incorporate the full range of potential factors and feedbacks, there is a strong scientific consensus that the increasing concentrations of atmospheric carbon dioxide and trace gases is creating a warmer planet with a different distribution of climate regimes. Computer models of climate, important yet imperfect tools. Earth's climate system is amazingly complex. Comprehensive state-of-the-art climate simulation models are among the tools used to develop possible climate change scenarios. Called general circulation models, they are based on fundamental laws of physics and chemistry and incorporate human and biological interactions. GCMs are used to simulate many variables, including temperature, rainfall, snow cover, soil moisture, winds, clouds, sea ice, and ocean circulation over the entire globe through the seasons and over spans of decades. In many other fields of study, hypotheses can be tested by direct experimentation in a laboratory or by field observations and measurements. However, this is often not possible in the study of climate. Rather, scientists must construct computer models of how our planet's climate system works. If we understand the climate system correctly and construct the model appropriately, the behavior of the model climate system should mimic the behavior of Earth's climate system. The blue band shows how global average temperatures would have changed due to natural forces only, as simulated by climate models. The pink band shows model projections of the effects of human and natural forces combined. The black line shows actual observed global average temperatures. As the blue band indicates, without human influences, temperatures over the past century would actually have first warmed and then cooled slightly over recent decades. Bands of color are used to express the range of uncertainty. Figure 20.31 separating human and natural influences on climate. Figure 20.31 full alternative text description. What factors influence the accuracy of climate models? Clearly, mathematical models are simplified versions of the real Earth and cannot capture its full complexity, especially at smaller geographic scales. Moreover, computer models used to simulate future climate change must make many assumptions that significantly influence predictions. They must consider a wide range of possible changes in population, economic growth, fossil fuel consumption, technological development, improvements in energy efficiency, and more. Despite many obstacles, our ability to use supercomputers to simulate climate is very good and continues to improve. Although today's models are far from infallible, they are powerful tools for understanding what Earth's future climate might be like. Concept checks 20.7. 1. Distinguish between positive and negative feedback mechanisms. 2. Provide at least one example of each type of feedback mechanism. 3. What factors influence the accuracy of computer models of climate? 20.8 Some consequences of global warming. Summarize some of the possible consequences of global warming. What consequences can be expected as the carbon dioxide content of the atmosphere reaches a level that is twice what it was early in the 20th century? Because the climate system is complex, predicting the occurrence of specific effects in particular places is speculative. It is not yet possible to pinpoint such changes. Nevertheless, there are plausible scenarios for larger scales of space and time. As noted, the magnitude of the temperature increase will not be the same everywhere. The temperature rise will probably be smallest in the tropics and increase toward the poles. As for precipitation, the models indicate that some regions will experience significantly more precipitation and runoff. However, others will experience a decrease in runoff due to reduced precipitation or greater evaporation caused by higher temperatures. Did you know? A scenario is an example of what might happen under a particular set of assumptions. Scenarios are tools that allow us to examine questions about an uncertain future. For example, future trends in fossil fuel use and other human activities are uncertain. Therefore, scientists have developed a set of scenarios for how the climate may change based on a wide range of possibilities for these variables. Table 20.1 lists possible effects of global warming based on the IPCC's projections for the late 21st century, ranked in decreasing order of certainty. Probabilities are based on the quality, volume, and consistency of the evidence and the extent of agreement among scientists. The risk associated with any of the projections in Table 20.1 is a combination of the probability of occurrence and the severity of the damage if it were to occur. This means that even projections labeled unlikely should not be ignored because if any of those events were to happen, the consequences would be extremely serious. Table 20.1 IPCC projections for the late 21st century. Table 20.1 full alternative text description. Sea level rise. A significant impact of human-induced global warming is a rise in sea level. As this occurs, coastal cities, wetlands, and low-lying islands could be threatened with more frequent flooding, increased shoreline erosion, and saltwater encroachment into coastal rivers and aquifers. How is a warmer atmosphere related to a rise in sea level? One significant factor is thermal expansion. Higher air temperatures warm the adjacent upper layers of the ocean, which in turn causes the water to expand and sea level to rise. A second factor contributing to global sea level rise is melting glaciers. With few exceptions, glaciers around the world have been retreating at unprecedented rates over the past century. Some mountain glaciers have disappeared altogether. A satellite study spanning 20 years showed that the mass of the Greenland and Antarctic ice sheets dropped an average of 475 gigatons per year. That is enough water to raise sea level 1.5 millimeters per year. The loss of ice was not steady but was occurring at an accelerating rate during the study period. During the same span, mountain glaciers and ice caps lost an average of slightly more than 400 gigatons per year. Research indicates that sea level has risen about 25 centimeters since 1870, with the rate of sea level rise accelerating in recent years. What about future changes in sea level? As Figure 20.32 indicates, the estimates of future sea level rise are uncertain. The four scenarios depicted on the graph represent estimates based on different degrees of ocean warming and ice sheet loss and range from 0.2 meter to 2 meters. The lowest scenario is an extrapolation of the annual rate of sea level rise that occurred between 1870 and 2000, 1.7 millimeter year. However, when the rate of sea level rise for the period 1993 to 2012 is examined, the annual change is 3.17 millimeters year. Such data show that there is a reasonable chance that sea level will rise considerably more than the lowest scenario indicates. This graph shows changes in sea level between 1900 and 2012 and projections to 2100, using four different scenarios. Currently, the highest and lowest projections are considered to be extremely unlikely. The greatest uncertainty surrounding estimates involves the rate and magnitude of ice sheet loss from Greenland and Antarctica. 0 on the graph represents mean sea level in 1992. Smart Figure 20.32 full alternative text description. Smart Figure 20.32 changing sea level. Watch video, NASA, melting ice, rising seas. Scientists realize that even modest rises in sea level along a gently sloping shoreline, such as the Atlantic and Gulf coasts of the United States, will lead to significant erosion and severe permanent inland flooding. If this happens, many beaches and wetlands will disappear, and coastal civilization will be severely disrupted. Low-lying and densely populated places such as Bangladesh and the small island nation of the Maldives are especially vulnerable. The average elevation in the Maldives is 1.5 meters. And its highest point is just 2.4 meters above sea level. The slope of the shoreline is critical to determining the degree to which sea level changes will affect it. As sea level gradually rises, the shoreline retreats, and structures that were once thought to be safe from wave attack become vulnerable. Smart Figure 20.33 full alternative text description. Smart Figure 20.33 slope of the shoreline. Because rising sea level is a gradual phenomenon, coastal residents may overlook it as an important contributor to shoreline flooding and erosion problems. Rather, the blame may be assigned to other forces, especially storm activity. Although a given storm may be the immediate cause, the magnitude of the destruction may result from the relatively small sea level rise that allowed the storm's power to cross a much greater land area. The changing Arctic. Watch tutorial, Shoreline Shift. The effects of global warming are most pronounced in the high latitudes of the northern hemisphere. For more than 30 years, the extent and thickness of sea ice have been rapidly declining. In addition, permafrost temperatures have been rapidly rising, and the area affected by permafrost has been decreasing. Meanwhile, alpine glaciers and the Greenland ice sheet have been shrinking. Another sign that the Arctic is rapidly warming is related to plant growth. A 2013 study showed that vegetation growth at northern latitudes now resembles that which characterized areas 4 degrees to 6 degrees of latitude farther south as recently as 1982. That is a distance of 400 to 700 kilometers. One researcher characterized the finding this way: it's like Winnipeg, Manitoba, moving to Minneapolis-St. Paul in only 30 years. Of the 26 million square kilometers of northern vegetated lands, about 40% showed increases in plant growth during the 30-year period ending in 2012. Smart Figure 20.34 Climate change spurs plant growth beyond 45 degrees north. Smart Figure 20.34 Full alternative text description. Arctic sea ice. Watch mobile field trip, climate change in the Arctic. Climate models are in general agreement that one of the strongest signals of global warming should be a loss of sea ice in the Arctic. This is indeed occurring. The map in Figure 20.35a compares the average sea ice extent for September 2016 to the long-term average for the period 1981 to 2010. On September 10 the extent was about 4.14 million square kilometers, the second lowest minimum of the satellite era, which began in 1979. Figure 20.35b, which shows year-to-year changes, clearly depicts the trend. Not only is the area covered by sea ice declining, but the remaining sea ice has become thinner and therefore more vulnerable to further melting. Models that best match historical trends project that Arctic waters may be virtually ice-free in the late summer by the 2030s. As noted earlier in this chapter, a reduction in sea ice is a positive feedback mechanism that reinforces global warming. Sea ice is frozen seawater. In winter the Arctic Ocean is completely ice-covered. In summer, a portion of the ice melts. This map shows the extent of sea ice in early September 2016 compared to the average extent of the period 1981 to 2010. The sea ice that does not melt in summer is getting thinner. The graph clearly depicts the trend in the area covered by sea ice at the end of the summer melt period. Smart Figure 20.35 Tracking sea ice changes. Smart Figure 20.35 Full alternative text description. The area covered by Arctic sea ice when it reaches its maximum extent in late winter is also declining. On March 24, 2016, the extent of sea ice peaked at 14.5 million square kilometers, the smallest maximum since satellite measurements started. Indeed, as of 2016, the 13 smallest maximums had all occurred in the preceding 13 years. Permafrost. Watch video, NASA, Arctic sea ice reaches 2014 minimum extent. Chapter 12 included a brief discussion of permanently frozen ground called permafrost that occurs in large portions of the high latitudes of the northern hemisphere. Mounting evidence indicates that the extent of permafrost in the northern hemisphere has decreased over the past decade, as would be expected under long-term warming conditions. Studies in Alaska show that thawing is occurring in interior and southern parts of the state where permafrost temperatures are near the thaw point. As Arctic temperatures continue to rise, some models project that near-surface permafrost may be lost entirely from large parts of Alaska by the end of the century. Thawing permafrost represents a potentially significant positive feedback mechanism that may reinforce global warming. When vegetation dies in the Arctic, cold temperatures inhibit its decomposition. As a consequence, over thousands of years, a great deal of organic matter has become stored in the permafrost. When the permafrost thaws, organic matter that may have been frozen for millennia comes out of cold storage and decomposes. The result is the release of carbon dioxide and methane, greenhouse gases that contribute to global warming. Thus, like decreasing sea ice, thawing permafrost is a positive feedback mechanism. Increasing ocean acidity. The human-induced increase in the amount of carbon dioxide in the atmosphere has some serious implications for ocean chemistry and for marine life. Recent studies show that about one-third of the human-generated CO2 currently ends up in the oceans. This additional carbon dioxide lowers the ocean's pH, making seawater more acidic. The pH scale is shown and briefly described in Figure 20.36. This is the common measure of the degree of acidity or alkalinity of a solution. The scale ranges from 0 to 14, with a value of 7 indicating a solution that is neutral. Values below 7 indicate greater acidity, whereas numbers above 7 indicate greater alkalinity. It is important to note that the pH scale is logarithmic, that is, each whole number increment indicates a tenfold difference. Thus, pH 4 is 10 times more acidic than pH 5 and 100 times more acidic than pH 6. Figure 20.36 Full alternative text description. Figure 20.36 The pH scale. When atmospheric CO2 dissolves in seawater H2O, it forms carbonic acid H2CO3. This lowers the ocean's pH and changes the balance of certain chemicals found naturally in seawater. In fact, the oceans have already absorbed enough carbon dioxide for surface waters to have experienced a pH decrease of 0.1 pH unit since pre-industrial times, with additional pH decrease likely in the future. Moreover, if the current trend in carbon dioxide emissions continues, the oceans will experience a pH decrease of at least 0.2 pH unit by 2100, a change in ocean chemistry that has not occurred for millions of years. This shift toward acidity and the resulting changes in ocean chemistry make it more difficult for certain marine creatures to build hard parts out of calcium carbonate. The decline in pH thus threatens a variety of calcite-secreting organisms as diverse as microbes and corals, which concerns marine scientists because of the potential consequences for other sea life that depends on the health and availability of these organisms. The potential for surprises. You have seen that climate in the 21st century, unlike during the preceding 1,000 years, is not expected to be stable. Rather, change is occurring. The amount and rate of future climate shifts depends primarily on current and future human-caused emissions of heat-trapping gases and airborne particles. Many of the changes will probably be gradual. Environmental shifts, nearly imperceptible from year to year. Nevertheless, the effects, accumulated over decades, will have powerful economic, social, and political consequences. Despite our best efforts to understand future climate shifts, there is also the potential for surprises. Due to the complexity of Earth's climate system, we might experience relatively sudden, unexpected changes or see some aspects of climate shift in unanticipated ways. Many future climate scenarios predict steadily changing conditions, giving the impression that humanity will have time to adapt. However, the scientific community has indicated that at least some changes will be abrupt, perhaps crossing a threshold, or tipping point, so quickly that there will be little time to react. This is a reasonable concern because abrupt changes occurring over periods as short as decades or even years have been a natural part of the climate system throughout Earth history. The paleoclimate record described earlier in the chapter contains ample evidence of such abrupt changes. For example, one such abrupt change occurred at the end of a time span known as the Younger Dryas, a time of abnormal cold and drought in the northern hemisphere that occurred about 12,000 years ago. Following this 1,000-year-long cold period, the Younger Dryas abruptly ended in a few decades or less. There are many examples of potential surprises, each of which would have large consequences. We simply do not know how far the climate system or other systems it affects can be pushed before they respond in unexpected ways. Even if the chance of any particular surprise happening is small, the chance that at least one such surprise will occur is much greater. In other words, although we may not know which of these events will occur, it is likely that one or more will eventually occur. The impact on climate of an increase in atmospheric CO2 and trace gases is obscured by some uncertainties. Yet climate scientists continue to improve our understanding of the climate system and the potential impacts and effects of global climate change. Policymakers are confronted with responding to the risks posed by greenhouse gas emissions, knowing that our understanding is imperfect. They must also face the fact that climate-induced environmental changes cannot be reversed quickly, if at all, due to the lengthy time scales associated with the climate system. Concept checks 20.8. 1. Describe the factors that are causing sea level to rise. 2. Is global warming greater near the equator or near the poles? Explain. 3. Based on Table 20.1, what projected changes relate to something other than temperature? Concepts in review: global climate change. 20.1 Climate and geology. List the major parts of the climate system and some connections between climate and geology. Key terms: weather, climate system, cryosphere. Climate is the aggregate of weather conditions for a place or region over a long period of time. Over time, if those conditions shift, the climate is said to have changed. Earth's climate system is a complex interchange of energy and moisture that occurs among the atmosphere, hydrosphere, geosphere, biosphere, and cryosphere. When the climate changes, geologic processes such as weathering, mass wasting, and erosion may change as well. 20.2 Detecting climate change. Explain why unraveling past climate changes is important and discuss several ways in which such changes are detected. Key terms: proxy data, paleoclimatology, oxygen isotope analysis. The geologic record yields multiple kinds of indirect evidence about past climate. These proxy data are the focus of paleoclimatology. Proxy data can come from seafloor sediment, oxygen isotopes, cores of glacial ice, tree rings, coral growth bands, fossil pollen, and even historical documents. Trees grow thicker rings in warmer, wetter years and thinner rings in colder, drier years. The pattern of ring thickness can be matched up between trees of overlapping ages for a long-term record of a region's climate. Oxygen isotope analysis is based on the difference between heavier O18 and lighter O16 isotopes of oxygen. Water molecules containing O16 evaporate more readily and thus are enriched in rain, snow, and glacial ice, leaving ocean water enriched in O18. Consequently, the O18-O16 ratio of ocean water rises during times of glaciation. During warm periods, glacial ice melts, and also the difference in evaporation between O16 and O18 containing water is smaller, so the O18-O16 ratio of ocean water falls. Oxygen isotopes can be measured in the shells of fossil marine organisms and in the water molecules that make up glacial ice. Glacial ice also traps small samples of the atmosphere in air bubbles. Why might the sediment core being collected by this oceanographic research vessel be useful to scientists studying climate change? 20.3 Some atmospheric basics. Describe the composition of the atmosphere and the atmosphere's vertical changes in pressure and temperature. Key terms: aerosol, troposphere, radiosonde, stratosphere, mesosphere, thermosphere. Air is a mixture of many discrete gases, and its composition varies from time to time and place to place. Two gases, nitrogen and oxygen, make up 99% of the volume of clean, dry air. Carbon dioxide, although present in only minute amounts, is an efficient absorber of energy emitted by Earth and thus influences the heating of the atmosphere. Two important variable components of air are water vapor and aerosols. Like carbon dioxide, water vapor can absorb heat given off by Earth. Aerosols are important because these often invisible particles act as surfaces on which water vapor can condense and are also good absorbers and reflectors of incoming solar radiation. The atmosphere is densest closest to the surface of Earth. It thins rapidly with increasing altitude and gradually fades off into space. temperature varies through a vertical section of the atmosphere. Generally, temperatures fall with increasing altitude in the troposphere, warm with altitude in the stratosphere, cool with altitude in the mesosphere, and increase again in the very tenuous thermosphere. This graph shows changes in an atmospheric element from Earth's surface to a height of about 140 kilometers. Which element is being depicted? Air pressure, humidity, or temperature? Show how this graph is used to divide the atmosphere into layers. Figure 20.10 to 1 Full alternative text description. 20.4 Heating the atmosphere. Outline the basic processes involved in heating the atmosphere. Key terms: albedo, greenhouse effect. Electromagnetic radiation is energy emitted in the form of rays, or waves, called electromagnetic waves. All radiation can transmit energy through the vacuum of space. Electromagnetic waves have different wavelengths. Visible light is the only portion of the electromagnetic spectrum we can see. Some of the basic laws that govern radiation as it heats the atmosphere are: all objects emit radiant energy, hotter objects radiate more total energy than do colder objects, the hotter the radiating object, the shorter the wavelength of maximum radiation, and objects that are good absorbers of radiation are good emitters as well. Gases are selective absorbers, meaning that each specific type of gas absorbs and emits certain wavelengths but not others. Approximately 50% of the solar energy that strikes the top of the atmosphere reaches Earth's surface. About 30% is reflected back to space. The remaining 20% that does not reach Earth's surface is absorbed by clouds and the atmosphere's gases. The amount of solar energy that is absorbed depends on its wavelengths and on the size and nature of the absorbing or reflecting substance. Radiant energy that is absorbed heats Earth and eventually is re-radiated skyward. Because Earth has a much lower surface temperature than the Sun, its radiation is in the form of long-wave infrared radiation. Because certain atmospheric gases, primarily water vapor and carbon dioxide, can absorb long-wave radiation, the atmosphere is heated from the ground up. The transmission of shortwave solar radiation by the atmosphere, coupled with the selective absorption of Earth's long-wave radiation by atmospheric gases, results in the warming of the atmosphere and is called the greenhouse effect. 20.5 Natural causes of climate change. Discuss hypotheses that relate to natural causes of climate change. Key term: sunspot. The natural functions of the Earth system produce climate change. The position of lithospheric plates can influence the climate of the continents as well as oceanic circulation. Variations in the shape of Earth's orbit, angle of axial tilt, and orientation of the axis all cause changes in the distribution of solar energy. Volcanic aerosols act like a sunshade, screening out a portion of incoming solar radiation. Volcanic sulfur dioxide emissions that reach the stratosphere are particularly important. Combined with water to form tiny droplets of sulfuric acid, these aerosols can remain aloft for several years. Volcanoes emit carbon dioxide. During times of especially large eruptions, such as those that produced oceanic lava plateaus during the Cretaceous period, volcanic emissions of carbon dioxide may contribute to the greenhouse effect sufficiently to cause global warming. Since Earth's climate is fueled by solar energy, variations in the sun's energy output affect Earth temperatures. Sunspots are dark features on the surface of the sun associated with periods of increased solar energy output. The number of sunspots rises and drops throughout an 11-year cycle. During the peak of the cycle, the sun puts out about 0.1% more energy than during the lowest part of the cycle. This small cyclical effect is not correlated with the current episode of global warming. 20.6 Human impact on global climate. Summarize the nature and cause of the atmosphere's changing composition since about 1750. Describe the climate's response. Key terms: trace gases, black carbon. Humans have been modifying the environment for thousands of years. Clearing or burning ground cover and overgrazing land have changed important climatic factors such as surface albedo, evaporation rates, and surface winds. Human activities produce climate change by releasing carbon dioxide, CO2, and trace gases. Humans release CO2 when they cut down forests or burn fossil fuels such as coal, oil, and natural gas. A steady rise in atmospheric CO2 levels has been documented at Mauna Loa, Hawaii, and other locations around the world. More than half of the carbon released by humans is absorbed by new plant matter or dissolved in the oceans. About 45% remains in the atmosphere, where it can influence climate for decades. Air bubbles trapped in glacial ice reveal that there is currently about 30% more CO2 than the atmosphere has contained in the past 800,000 years. As a result of extra heat retained by added CO2, Earth's atmosphere has warmed by about 1 degree Celsius since the late 1800s, most of it since 1980. Temperatures are projected to increase by another 2 degrees Celsius to 4.5 degrees Celsius in the future. Trace gases such as methane, nitrous oxide, and CFCs also play significant roles in increasing global temperature. When emitted due to human activities, tiny liquid and solid particles suspended in the air, called aerosols, have an effect on global climate. Many aerosols reflect a portion of incoming solar radiation back to space and therefore have a cooling effect. Some aerosols, called black carbon, absorb incoming solar radiation and warm the atmosphere. When black carbon is deposited on snow and ice, it reduces surface albedo and increases the amount of light absorbed at the surface. Do aerosols spend more or less time in the atmosphere than greenhouse gases such as carbon dioxide? What is the significance of this difference in residence time? Explain. 20.7 Climate feedback mechanisms. Contrast positive and negative feedback mechanisms and provide examples of each. Key terms. Climate feedback mechanism, positive feedback mechanism, and negative feedback mechanism. A change in one part of the climate system may trigger changes in other parts of the climate system that amplify or diminish the initial effect. These climate feedback mechanisms are called positive feedback mechanisms if they reinforce the initial change and negative feedback mechanisms if they counteract the initial effect. An example of a positive feedback mechanism is the melting of sea ice due to global warming. A decrease in sea ice exposes more low albedo open water, which increases warming, which causes more sea ice to melt, and so forth. Cloud production can constitute a negative feedback mechanism. Warming increases evaporation, which leads to the formation of more clouds, which causes cooling. Computer models of climate give scientists a tool for testing hypotheses about climate change. Although these models are simpler than the real climate system, they are useful tools for predicting the future climate. This icebreaker is plowing through sea ice in the Arctic Ocean. What spheres of the climate system are represented in this photo? How has the area covered by summer sea ice been changing since satellite monitoring began in 1979? How does this change influence temperatures in the Arctic? 20.8 Some consequences of global warming. Summarize some of the possible consequences of global warming. In the future, Earth's surface temperature is likely to continue to rise. The temperature increase will likely be greatest in the polar regions and least in the tropics. Some areas will get drier, and other areas will get wetter. Sea level is predicted to rise for several reasons, including the melting of glacial ice and thermal expansion. Low-lying, gently sloped coastal areas are most at risk. The extent and thickness of sea ice in the Arctic have been declining since satellite observations began in 1979. Because of the warming of the Arctic, permafrost is melting, releasing CO2 and methane to the atmosphere in a positive feedback loop. Because the climate system is complicated, dynamic, and imperfectly understood, it could produce sudden, unexpected changes with little warning. Give it some thought. 1. refer to Figure 20.1, which illustrates various components of Earth's climate system. The boxed labels represent interactions or changes that occur in the climate system. Select 3 of these boxes and provide an example of an interaction or change associated with each. Explain how these interactions may influence temperature. 2. When this weather balloon was launched, the surface air temperature was 17 degrees Celsius. The balloon is now at an altitude of 1 kilometer. What term is applied to the instrument package being carried aloft by the balloon? In what layer of the atmosphere is the balloon? If average conditions prevail, what is the air temperature at this altitude? How did you figure this out? 3. Figure 20.15 shows that about 30% of the sun's energy intercepted by Earth is reflected or scattered back to space. If Earth's albedo were to increase to 50%, how would you expect Earth's average surface temperature to change? Explain. 4. Volcanic events, such as the eruptions of El Chichón and Mount Pinatubo, have been associated with drops in global temperatures. During the Cretaceous period, volcanic activity was associated with global warming. Explain the apparent paradox. 5. The accompanying photo is a 2005 view of Athabasca Glacier in the Canadian Rockies. A line of boulders in the foreground marks the outer limit of the glacier in 1992. Is the behavior of Athabasca Glacier shown in this image typical of other glaciers around the world? Describe a significant impact of such behavior. 6. Motor vehicles are a significant source of CO2. Using electric cars, such as the one pictured here, is one way to reduce emissions from this source. Even though these vehicles emit little or no CO2 or other air pollutants directly into the air, can they still be connected to such emissions? If so, explain. 7. During a conversation, an acquaintance indicates that he is skeptical about global warming. When you ask him why he feels that way, he says, "The past couple of years in this area have been among the coolest I can remember." While you assure this person that it is useful to question scientific findings, you suggest to him that his reasoning in this case may be flawed. Use your understanding of the definition of climate along with one or more graphs in the chapter to persuade this person to re-evaluate his reasoning. 8. A 2015 report by the National Research Council recommends that climate intervention research be conducted to explore strategies to help offset global warming. One strategy would involve injecting aerosols into the stratosphere. A. Explain how such an aerosol strategy might influence global warming. B. What natural cause of climate change operates on the same principle as the one you describe in your answer to Part A? 9. This large cattle feedlot is in the Texas Panhandle. How might consuming less beef influence global climate change? Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text.